Alright guys, welcome to my tutorial. Today I'm going to walk you through a brief introduction to Gauss's law. Actually, before I even start, let me just erase all of this, and let's just focus onto the symbol on the left here, phi. And this denotes flux, more specifically electrical flux. I'll give you a helpful example to visualize this. So let's say we have an imaginary surface, alright, in space. It's a flat plane. And let's call this our flux catcher. Alright? It is a very special type of surface. It only allows stuff to pass through the bottom of it. So let's have a vector pointing up. Let's call it the surface area vector. And let's say there's also a uniform electric field coming in from the bottom that is perpendicular to this surface. Oh, and as well, this vector is normal to the surface as well. Essentially what flux is measuring how much stuff is passing through a given area. And in this example, our area here is given by A. Now we can measure the total amount of stuff flowing through this surface by simply just multiplying E times A, right? And that gives us our flux. Now, I want to walk through another example where we slowly rotate our flux catcher until the angle between our area vector and the electric field is 90. And notice when we do this, it catches less and less and less until eventually it's 0, right? This angle here is 90. Now, there is a mathematical intuition behind this. So let me bring back the original integral from the first page, which is simply the electric field vector times the dot product of dA. Now, the dot product simplifies to E times A, the magnitude of both of the vectors, times the cosine of the angle between these two. Now, in this specific example, it's 90. And cosine of 90 is 0, so this equates to 0 total flux. Now, what if I rotate this even more? So let me just go ahead and do that. And as I do this, our area vector is pointing down until eventually the angle between this and this is 180. And essentially, cosine of 180 is negative EA. Now let's take a look back to our original integral here. And why exactly are we integrating? So, since this plane is flat, our flux catcher, each of these field vectors are equidistant to each other from whatever source it's from, meaning that they have the same magnitude. So the E field is constant. So we can just rewrite this integral to be E times the area of dA, alright? Now, essentially, what dA is just an infinitesimal change of the surface area. Here's dA. We're adding each of these changes, and they are each being multiplied by E at the very specific point where they are located at. Alright? Now, this is just a simple integral. The integral of d anything is just the variable itself. So this equates to E times A. Now, what if we had multiple of these flux catchers arranged into a shape? Well, we can do that. So let me just draw you a cube here. Now, it is a closed surface. There are no gaps located in here. And let's say there is an electric field pointing to the right here. Let's call it E. And for a closed surface, the surface area vectors are always pointing outward. So let's call this one A. Down here, A. Right here, pointing to the left here, A. So on and so forth. Now, let's just walk back to what we did before. So this here, since this is perpendicular and this is also perpendicular, the angle between them is 180. So this is just negative EA. Same goes here. The angle between these two is 0. So it just equates to be EA. Now what about these four other sides? Well, here it is perpendicular here, so 90, as well as right here is also 90, so on and so forth. So these four surfaces are all 0. This equates to 0. And what does this tell us? Well, here's where I want to bring in the third part of our equation here, which is just Q enclosed over epsilon naught. Now, epsilon naught just being a constant of the universe, the permittivity of space. And this is telling us that there is no enclosed charge in our surface here, which is true. There's just an electric field, and electric fields are ubiquitous in space. Now, what if we had a charge enclosed by our imaginary surface? What would that look like? So let me just go ahead and draw a positive particle Q here with its electric field lines radiating outward like this. Now, can you imagine a surface where each point on that surface is equidistant from the center and is perpendicular to this vector right here? Well, if you said a sphere, good job. So let me just draw one here. If I can draw one, okay, there we are. And with its surface area vector pointing out, it is the angle between this and this is 0, as well as it having a radius r. Now let's bring back our original integral here, and notice that our area has changed. It's no longer a flat sheet of paper. So the surface area of the sphere is denoted by 4 pi r squared. And let's just set that equal to our enclosed charge over epsilon naught. Now, what if we wanted to solve for the electric field? Well, we can just divide this by that, and we end up having 4 pi squared epsilon naught. This looks very familiar. Hang on. Coulomb's law? How weird.